Now we're recording. Okay. So I'm going to run through a quick review, maybe half an hour, then happy to answer questions. I'll stick around afterwards too to answer a few questions. We'll also do some review in class tomorrow. We'll do a quiz show where we'll go through population distributions and some hypothesis tests in an entertaining format, I hope. Okay, so let me begin with this. So I hope you all got the review sheet. So there's one sheet that's a list of the topics, and then another sheet that's this kind of graphical comic book description of what's happening in the class. And I'd like to use this to start to talk about what it is we're hoping you have learned so far. So you have the idea of a population, and it's got some parameters, mean, standard deviation, maybe lambda, and so on, depending on the kind of population. We take a sample of n of those elements, and then we do some calculations. And we calculate the sample mean, and we calculate the sample variance. And it's n minus 1 if it's a sample, if it's n if it's the entire population. And then we want to know, for our data, compared to some given assumption about the population typically, how far off am I? So we need to know these distributions. And these sampling distributions are really the key to statistics. If you know how to calculate these, the rest of it usually gets pretty easy. Okay? So let's look at the sampling distribution for X bar. And we often have a normal, so let's start out and assume, I'm going to do assumption number 1, that this is a normal population, whereupon this is going to be normal as long as I know either the standard deviation of the population or I have enough samples, n is bigger than maybe 30, that the central limit theorem applies. So let me go through that again. I assume I've got a normal population, I take my sample, I calculate the sample mean, and then I ask what's its distribution. And if either I know the population or I have enough samples, then this is going to be normal. So let me call this case 1A. And in that case, the mean of this distribution is going to be the population mean. And the width, I'll call it sigma of x bar, is equal to sigma for the population divided by the square root of n. And this is, of course, the standard error. Okay. Now, let's talk about what happens if I have a normal population again, but I don't satisfy these conditions. So I don't know the population, and my population isn't big enough. I'll call that case 1B. So I have sigma pop unknown, and my n is less than or about equal to 30. Okay, what's the difference now? What do I do?
Use the t-distribution?
Yeah, I just go to the t-distribution. So this is 1a. So 1b is go to t. Okay. So I'm trying to do this as a kind of a decision process. So if you've got a problem, you can go through these cases and see where you wind up. Okay. Number 2. Suppose it's not normal. I don't care what it is. It can be any funky thing. It could be a binomial that's skewed way off to one side. It could be some weird numerical thing that, is hard to describe analytically. Whatever, it's not normal. What do? Okay. So this is case 2. So suppose my n is big again. It's bigger than about equal to, say, 40. If my population is pretty unimodal, not a lot of outliers, not a lot of skewness, then I can probably get away with a smaller number, 30, maybe even 20. If it already looks kind of normal, if it's skewed off to one side, I might need to go up to 50. But anyway, I have enough samples. What do I do now? What kind of distribution is this going to look like? Okay, so the central limit theorem says that this is normal. So this means all the rest of my machinery, this is all true here as well. I have to estimate my x bar as approximately equal to s squared. Oh, and I should have added that here too, that my population is approximately equal to the sample standard deviation of x bar. Oh. Okay. So if it's not normal and I get a bunch of samples, it's cool. I can treat this as normal. All my z-tests will work for me here. Okay? Now, I'll call that 2a again. What about 2b, where n is small? It's less than, roughly 40. What do I do then? Get more data, so it gets bigger. There's always one good approach. But more realistically, you have to use the exact distribution. Okay, and for this, I can calculate, my x bar is equal to the sum of my xi's over n. So if these are binomial random variables, then I can calculate what this is going to look like. If they're Poisson, I can use the normal approximation that's large. We didn't go through this. Basically, you either have to use the exact distribution or give up. Say you don't know how to do this, okay? In some cases, like the binomial we've actually looked at, we've done cases where we use the binomial distribution here. Poisson, we only did the case where we looked at the large approximation, the large number approximation where we could use the central limit theorem. Okay, so really the only case in this world is binomial that we know how to solve at this point. Yeah?
And that's n times p, right? The mean is equal to n times p?
For binomial, yes.
And
yeah.
That lowest formula that you wrote down there, is that always a substitute for these other formulas? Or when does that one apply?
This is always the definition of the sample mean. Okay, but now what I need to know is the distribution of the sample mean.
Oh, I see.
Right, I need to know the shape of this curve, and if I've got a binomial that's skewed, p is equal to 0.1 or something like it is here, then this is also going to have a funny shape to it if n is small. If n gets big, it'll look normal, life is good. But if n is small, it's going to be funky, and then I have to calculate it. And again, the only one where we've really done that is binomial so far. Okay. Okay. So that's the story for the sampling distribution for the sample mean. And again, the bottom line here is that I'm going to use this to estimate my population parameter, usually my population mean. That's the goal, is I want to get some idea of what the population mean is like, know how well I know it, confidence intervals, hypothesis test. And I use x bar for that, but to understand how well I'm estimating, I need that sample distribution so I understand what my spread is here. Okay. And the other important thing to notice here is what happens with n. So as the number of samples goes up and up, this gets skinnier and skinnier as 1 over the square root of n. So you need a lot more data. You need 100 times more data to get this to be 1/10 of its former width in estimating the sample or the population mean. Okay? Okay. So that's the story for the mean. Let's see. I think I can leave all this in place up here. So now I want to know the sampling distribution for the sample variance. And you know, the sample standard deviation is just the square root of that. And this is the useful number usually, but we work in terms of S squared because we work in terms of chi-squared. But anyway, so what's the sample distribution for this look like? It's chi-squared, and it usually looks something like this. It's asymmetric, it's all positive. And if we started with a normal population here, then we're going to get the chi-squared, okay? And then we can do this, use this. We haven't done hypothesis tests yet, but we have done confidence intervals. So, and we'll go through that in a second. But again, it's the sampling distribution of this, and then we use this to predict or estimate the population. Okay, so we come up with some value. Our best guess for the population standard deviation is going to be S squared. Okay. Okay, what happens if I have n bigger, n small? What difference does it make for the sampling distribution? Remember, chi-squared has a degrees of freedom. So we have chi-squared, and we have our alpha or whatever, and we have k. And k is n minus 1. So the shape of this curve changes as my n goes up and down. But that's the only effect. It isn't like the mean, where when the number gets small, I need to use t. Here I always use chi-squared, but it's kind of got this built-in method of accounting for larger and smaller numbers of samples. Okay. So this is what my sampling distribution looks like if the population is normal. What about the case where the population is not normal? What do? Call a statistician. Okay, these are complicated techniques where, think about what you have to do now. You have to understand how, as you draw samples from a non-normal population, you know, skewed binomial, who knows, whatever, how is that going to affect the standard deviation of the sample? So that every time I draw a sample, I get a different number. Okay, so it gets complicated when it's not normal. For the purposes of this class and for most analysis, you need to have a normal population to be able to do much inference on the standard deviation. Okay? So you can rest assured you will not get questions about this. Okay, the next and last thing I want to do with this sheet, everybody have this? Can I erase it? Okay. Okay. I want to talk about assumptions. Okay, what kind of assumptions did we make going along the way here? Well, the one I just pointed out, let me be very clear about, for using t squared and chi-squared, we have to have a normal population. Okay. Another assumption that's throughout is IID, which is like saying it's a random sample. Anybody remember what IID stands for? Okay, independent, identically distributed. Okay, so we make that assumption for all of this. And how about independent? So if I go out, suppose I want to get an estimate of the approval rating of President Trump, and I'm lazy, I just go out on the streets of Cambridge and I ask people, do you approve of the president? Will that give me a random sample of national opinion on President Trump? No, because that is certainly not identically distributed with the population we're looking for. So we'd have to go to Oklahoma and Alaska, and you want to get a real representative sample there. Okay. suppose I have a small population like this class, and I want to figure out who understands some concept, so I'm going to test a fraction and then infer. So we have, I think, 34 students and 35 students in the class. Suppose I pick 18 and sample them. Does that qualify? Why not? I see shaking heads, why not?
People who are here.
I'm sorry?
I don't know. Okay.
Is there a rule thinking about like if you have more than 25%?
Correct. So now I've taken away so much of the population that the next one I draw is influenced by the fact that I've already taken half the class. And so what I have already sampled is influencing the next one. And there are corrections for this, we're not going to go there. But that's a case where it's not identically distributed again. Okay. So the idea here, the concept that I think is, or the way of phrasing this that's most useful is, every member of the population that you're inferring about is equally likely to be selected. So every member of the United States is equally likely to be selected when I try to figure out the president's national approval rating, that kind of thing. Okay, there are a bunch of little assumptions, you know, on particular cases. I'll try to mention those when I go through some examples here as well. Any questions so far? I'm going to work, my plan is to work two problems. One's a confidence interval and one's a, I'm sorry, one is a hypothesis test, one's a confidence interval. And then I think that covers most of it. If I can find the example I worked out. Uh-oh. This is interesting. Yep, here it is. Okay, so okay, so this is an engineering example. Suppose we have building sprinklers. You know, these are the things in the ceiling in commercial buildings and big apartment buildings where if there's a fire, there's a little soft metal piece that melts and releases water. And they're tremendously effective. One of my colleagues told me, it's been a few years ago, that there have never been multiple deaths in a US building that has sprinklers. One person may die, but they're so effective at giving people time to get out of the building that there's never been a case of multiple deaths in a sprinkled building. It's pretty amazing when you think about it. Okay, so the manufacturer here, and one of the key parameters of these things is at what temperature they activate. And you want them to melt at a pretty low temperature. You don't want to have flames right underneath it for the sprinkler to activate. You want it to go off when there's like flame nearby, you know, so the critical temperature when they activate is pretty important. Now suppose that the manufacturer claims that the temperature for activation is equal to 130 degrees F, which sounds low, but is apparently used. And also that they give some mention of the tolerance. The distribution of the temperatures of activation is normal, and the standard deviation, I should say, of the population is 1.5 degrees. Okay, well, a fire marshal tests this for 9 of them and gets the average temperature for activation as 131.1 degrees Fahrenheit. So, is the manufacturer correct? How would we know? How would we talk about this? So this is another one of these statistical problems where there's variability. You can't say, yes, the manufacturer is correct, or no, the manufacturer is wrong, unless you were to test every single sprinkler they ever manufactured. So instead, we do some kind of a test. What kind of a test would we do here? Come on, this is easy. Hypothesis test. Yeah. Okay, what kind of a hypothesis test? What kind do we have? So we have t-tests, we have z-tests, we have chi-squared tests. We have one-tailed, we have two-tailed. What do we like for this one?
I think it would be a one-tailed z-test.
One-tailed, okay, and a t.
Yeah,
And
Z,
why t? Let's start with t.
Actually, T, yeah. T. I meant T.
I'm sorry? I don't hear well, so it's easy for me to miss. I'm sorry.
No,
T.
yeah.
Yeah, okay. So we'll do a hypothesis test using the t distribution. Why t?
Small size and it's small.
N is small, yeah. Okay. And why one-tailed?
We only care if it's like too low.
Or too high? Too low means they go off too often. Too high would mean they don't go off when they should. What do we think?
I think it would only be one-tailed because it's not a big problem if they go off too early.
Ooh, imagine cleaning up that mess. That would be bad. 1 degree, I don't know how much difference 1 degree makes. Yes?
Yeah, so I still think it'd be one-tailed because it'd still be like really hard to get up to that temperature to potentially like set it off too early. I don't know, I feel like that'd be,
Yeah, I guess if you look at global temperatures, you know, the temperature range in a room, it doesn't get up to 130, at least not in Boston, that's for sure, very often. Yeah. Okay, again, whether it's one-tailed or two-tailed, sometimes it's clear, like, is this better? Then it's clear, oh, it has to be higher, that's one case. But often it's not clear. In this case, I would use a two-tailed test. And the reason is we want to know if the manufacturer is correct, and there could be consequences going either way. Again, if it went off too soon, that'd be bad. If it went off too late, that'd be bad. So depending on, you know, you need more details than just correct to make a real thorough decision. But in general, two-tail is the place you go unless you've got a strong reason to go with one-tail. Yeah.
I had a question about why, so if we know the standard deviation of the population, even if the sample size is small and we know that the sample or that the population is normal?
Oh, you're right, yes. We could use I forgot I gave you the population distribution. You're completely correct. That the first version of this problem, I left that out, and then I put it in. So you're correct. It would be Z in this case. And again, I'd say two-tail because there's potentially something wrong in both directions, and this is where you would have a large argument with your boss and with the the customer and everybody else to figure out which kind of test you should really do. But when in doubt, two-tail is usually the choice.
What's the other option besides hypothesis?
It would be a hypothesis test to answer this. But we know a number of different statistical procedures, right? We know confidence intervals, we know hypothesis tests. So in this case, would be to answer this question would be a hypothesis test. Okay, so hypothesis test, we need two hypotheses. The null hypothesis, the one we want to accept unless there's strong evidence, or we want to believe the manufacturer unless there's strong evidence they're wrong, is that the mean temperature here is, as they say it is, 130 degrees. And the alternative is that for a two-tailed test, it's not equal to 130. And again, that means it could either be too high or too low. Okay. Now, the next thing I recommend doing at this point is a sketch of the distribution to make sure you understand what's going on. So I'm going to erase one word here so I have room. So we were told it's normal, so we know this is the null hypothesis sampling distribution. So this is the distribution for my average of the temperatures for the 9 tests I did. Okay. And we know this is centered up around our mean of 130 degrees. And we'd like to figure out what's the standard deviation of this distribution. And the standard deviation for t-bar is going to be the population, standard deviation divided by the square root of n. And we actually know what that is. Yeah?
wait, What is this T-bar in 131.1?
This is the sample average. We tested 9. So I had 9 different values. I had 130.2, 129.6, 132.0, you know, and I averaged them all, and this is what I got. It's the usual idea of sampling up, averaging up the different samples. Okay. Other questions? Okay. So I can calculate this. I'm told, when I remember, that this is 105 degrees. This is the square root of 9. What convenient numbers? This is then going to be 1.5 over 3, so this is 0.5 degrees. So now I can increment across here in units of standard deviation. So now I can say 1 standard deviation, 2 standard deviations, 3 standard deviations, and so on. This is going to be 130.5. This is going to be 131. This is going to be 131.5, and so on, where there's a standard deviation between each one of these. And of course, it goes the other way too. This would be 129.5, and so on, down the other way. Okay. So right now, my data comes in where? Well, my T-bar is 131.1, so here's 131. So here is my statistic from my data. Statistics are calculated from data, so that's my statistic. So I'm just outside 2 standard deviations. So we already know the answer, okay? But let's go ahead and calculate this. So I'm going to draw a second axis on here. So this is the t-axis. These are in physical units, the things we actually measure. This is the z-axis that corresponds to this. And for z, the center is always at 0, the standard normal, centered at 0. Yeah?
Are you saying the standard deviation is 0.5? Or
The standard deviation of the sampling distribution, not of the
okay,
population,
sorry.
right?
Okay,
Yes,
sorry.
got to keep these separate. This is the key
Okay.
idea of the whole course so far. And this is the standard error. They made up a new word for it because it's so important and it's easy to confuse with the standard deviation. So the standard error is the standard deviation of the mean, sampling distribution, and it's the population standard deviation divided by the square root of it. Good. Okay, back to the z-axis. Well, the z-axis units are easy because they're standard deviations. So 130 degrees corresponds to 1. 131 corresponds to 2. 131.5 corresponds to 3, and so on. 129.5 is minus 1. Okay. Now, how do I decide whether to reject or not? I need to figure out what's the probability in the tail and see if my data is so far out that it's in that very unlikely tail. So I didn't say what level I'm going to use here. Let's pick for this test. Alpha is 0.05. So this is a 95% confidence level hypothesis test. Okay, so there's some rejection region out here where the probability in this tail is equal to 0.025. I hate this big chalk, but I'm told it looks better on camera, which is alpha over 2. Now I have a two-tailed test, so I have the same thing over here, right? This is probability of 0.025, my 5% over 2. So now I need to figure out if my data, my average, my sample average is in that tail, which would mean it's really unlikely. If my null hypothesis is true and I get data that's in the tail, whoa, it's really unlikely that I would have gotten that kind of a value if the hypothesis was true. So I do that using the z, and the idea here excuse me, is that I calculate my z is equal to x bar minus mu sigma over the square root of n. Whenever you see the square root of n under a sigma, you know this is the population, and that combination is the standard error.